In this lesson, we're going to look at the rational root theorem. In order to understand its importance, let's consider this previous question that we have looked at before. We're told to find all the zeros of f of x given that x plus 5 is a factor. Okay, so this is cubic and it has 4 terms. So potentially, maybe it factors, and we do know some factoring methods, but one of the things we learned to do was, if we know that x plus 5 is a factor, the corresponding zero would be -5, and we learned to set up synthetic division and figure out the depressed polynomial. So we started by bringing down 1, we'd multiply, add, add, and we get a remainder of 0, which we know we should get because we were told that x plus 5 is a factor. So the remaining polynomial would be 1x cubed plus 4x plus 3, and we already knew that x plus 5 was a factor. So our polynomial would be equal to x plus 5 times that polynomial. Then we could factor x squared plus 4x plus 3 further. You could do that off on the side. Those of you that prefer the tic-tac-toe method, you set up your board, and factors of x squared would be x and x. Factors of 3 would be 3 and 1, multiply across, and check it by adding, and it works. So this factors into x plus 5, x plus 3, and x plus 1. And from here, we would know that my zeros would be x equals -5, -3, and -1 after I apply the zero product property. But notice what we were given from the very beginning. We were given a factor as a starting point. But this begs the question of, well, what do we do if we don't have a starting point? How do we find the zeros of a polynomial when we aren't given one to start? Which leads me to the rational root theorem or the rational zero theorem. René Descartes is credited with coming up with this theorem, the same French mathematician who came up with the good old coordinate plane. It says that if f of x has integer coefficients, then every rational zero of that function is in the form of p divided by q, where p is the factors of your constant term and q is the factors of the leading coefficient. So you may think, well, what does that even mean, okay? And why is this so amazing that René Descartes came up with this? So think about your x-axis. That's where your zeros are. So if you have some sort of polynomial function that cuts through it multiple times, and you're trying to find one possible number that is a zero, so you can start your synthetic division, if you have an infinite amount of x values you've got to check, that's a lot. Well, René Descartes figured out that that list is in the list of p divided by q. So he took it down from an infinite amount of zeros on the x-axis that could potentially work, down to just a finite list that sometimes might only be 10 numbers. You know what? Even if it's 50, going from infinite down to 50 is pretty remarkable. Now let's show you what I mean by the list of p divided by q. So my leading coefficient here is 1, and my constant term is 12. So I'm going to begin by looking at 12, and I'm going to list all the factors of 12, okay? That's going to be my list of p. So factors of 12 would be 1 and 12, 2 and 6, 3 and 4, and there's my entire list. Notice I ordered from least to greatest. Works for me. I also have to tell you that, well, -1 and -12, -2 and -6, -3 and -4. So here's how I handle that. I slap a plus or minus sign and put my list in set notation. And there I see that I have both the positives and negatives. Now, my factors of q. Q comes from your leading coefficient. So my factors of 1, well, that would be 1 times 1 and -1 times -1. So I also write plus or minus 1. So my list of p divided by q is, we'll just take every possible combination of this divided by 1. Well, that's just going to be equal to, if I divide by 1, I'm getting the same list as I had up above. So it's plus or minus 1, 2, 3, 4, 6, and 12. So what's this mean? How many values is that? 1, 2, 3, 4, 5, 6. But double it because we got the negatives. That means René Descartes narrowed down your infinite amount of places it could cross the x-axis down to just 12 possible if they are rational. Now I need to point out that it's possible that there'd be irrational ones like the square root of 3. They would not be included in this list, but if rational ones exist, they're here. Let's demonstrate with the second example. So P and Q would be kind of nicer if it was alphabetical order, wouldn't it? But let's list our factors of P. So of negative 10, well, that would be 1 and 10, 1 and negative 10, 2 and negative 5, and that's it. Now notice I only listed positive. Why is that? Because, well, I'm going to put that plus or minus out front because maybe it's negative 1 and positive 10 or positive 1 and negative 10. So it's going to include both positives and negatives all the time. Now for Q, my factors of 4 would be 1, 2, and 4 are the 3 values, but again, it's those and their opposites. So now what about my list of P divided by Q? All right, so that means I'm going to first take each of these numbers and divide it by 1. So when I divide by 1, well, that's going to give me 1, 2, 5, and 10 again. Now I'm going to divide by 2, right? So I'm going to list those in yellow. So that would be 1/2. Well, 2 over 2 is going to reduce to 1, so I'm not going to write that a second time. But then I have 5 over 2, and 10 over 2 would reduce to 5, and that's already in my list. So I'm going to get rid of that. I don't need it twice. And now I'm going to divide by 4. So that would be 1 divided by 4 is 1/4. 2 divided by 4 is 1/2, and that's already in my list. 5/4, and then 10/4 would reduce to 5 over 2. So there's my entire list. So it may look like a lot of numbers you'd have to check to see if they work. But again, you've gone from an infinite amount down to 1, 2, 3, 4, 5, 6, 7, 8, and their opposites, 16 possible numbers to check. Much more reasonable than an infinite amount. All right, proceed to the self-check and make sure that you can identify the P's and Q's.